Have you ever binged on Netflix and completely lost track of time? I have. Recently. Like, last weekend. And just as I finished an episode, my buddy Chris walks in and he's like... And I'm like, I don't know, I guess I've been watching for a couple hours. He doesn't believe me, so he looks at my viewing history. 36 episodes, he says, and each episode is about 45 minutes without commercials, so that's 1,620 minutes or 27 hours. Anyway, as he walks off in disgust, I realize that what he did was kind of like radiometric dating, and that I should use that analogy up next on PS 100. Geologists use radiometric dating to figure out how long ago a geologic event happened, and it's a pretty complex, sophisticated system, but the principles behind it are pretty simple. When elements decay, they don't just disappear. They change into something else, and just like Chris calculating how long I sat in front of the TV, by counting up the number of finished episodes, geologists calculate how long a rock has been in a specific state by figuring out how many of its original elements, or parent elements, have decayed to produce new daughter products. For example, we know how long it takes for potassium to decay and become argon gas, so if we can figure out how much gas is trapped inside a rock's crystals, we can calculate how long that rock has been producing argon. But there's a catch. Mother Nature keeps resetting our radiometric clock, and she keeps doing it by cranking up the heat. Though the elements in a rock are constantly decaying, the daughter products of that decay may escape when the rock is above a temperature we call the closure temperature. When a rock is above the closure temperature, daughter products are lost faster than they're produced. And if there's nothing there, we've got nothing to calculate. So radiometric dating doesn't tell us how old the elements in a rock are, it just tells us how long the rock has been below a closure temperature. Let's look at a real-life example. The granite found in Utah's Wasatch Mountains was once buried far below ground, and that granite didn't cool below its closure temperature until collision forces pushed it up through the Earth's crust and made mountains out of it. Of course, the Wasatch Mountains didn't come bursting out of the ground all at once. They're still rising gradually above the valley floor, actually. So when scientists analyzed some Wasatch granite, they found that samples at the top of the mountain gave ages that were much older than the samples at the bottom. That's because the top samples were chilling near the surface, while the bottom samples were still buried roasty toasty deep in the earth. So how is this information useful? Well, radiometric dating can tell us a lot of useful things. In this case, subtracting the radiometric dates of the bottom samples from the dates of the top samples, it tells us how long it's taken for the Wasatch Mountains to grow. And then using the height of the mountains and the time obtained from the ages, we can calculate how fast the mountains are being uplifted. On average, they're going up by about 1 millimeter each year. Other studies show us how often an earthquake has made the valley floor suddenly drop and the mountains rise, which could help us predict the next big one. These big earthquakes happen on average about once every 2,000 years on each segment of the Wasatch Fault. With about 10 segments along the entire fault, that means that we should expect a large earthquake about once every 200 years. That seems like useful information to me, especially when you consider that it's been about 169 years since the pioneers first settled along these Utah mountains, and we haven't had a big earthquake since then. As you can imagine, scientists are starting to worry about the fault. That's it for this episode. Now be sure to check out the links in the description below, and for more science and research opportunities for BYU undergrads, visit science.byu.edu.